All right, great. You guys pointed out my mic was off. Okay, so let's go back. So final call for homework number 11. That's due tonight. Okay, and then number 12 will be due on Monday. Final exam will be on Wednesday next week. Okay. All right. So and then that's during our lecture time. It's not a scheduled by the university, so we don't have to come back for the Monday during the Thanksgiving week. Okay, so then we will be done on Wednesday next week. Okay. All right. So let's take a look what we learned last time. So last time we compare simple harmonic motion and circular motion. Okay, so basically, as circular motion, all right, if it's uniform, circular motion, that means angular speed is uniform, then the trajectory of it in one dimension will be a single harmonic motion. It will be going back and forth, okay? So that's how you can relate the two, all right? So, and then at the same time, if you can set it up that if you have a spring attached to a mass attached to a spring, and then also a circular motion, if you can set up the amplitude for the mass attached to the spring, it's the same as the radius, and then the frequency of the circular motion match up with the angular frequency of the simple harmonic motion, then they will be synchronized at any time. Okay, so that means projection of the circular motion in one dimension will match up the position of the mass. Okay. All right. So, and then from circular motion, we can see that, so if you have circular motion, then projection of it will be the, for example, in the x direction should be the same as the cosine function as we had in the simple harmonic motion, okay? And the same thing for velocity will be a sine function, and then acceleration will be again, a cosine function, okay? So that's what we check. And last time, so and then we also talk about the pendulum. So for a pendulum, simple pendulum, it's actually a point mass. You can actually model it as a point mass attached to a spring. So then in that case, let's also list restoring force minus mg sine theta when you pull it certain distance away. Okay, and compared to the mass attached to a spring where F is equal to minus kx, so then this two forces has similar expression. If you take small angle approximation, if the angles are small, then just replacing mg or replacing the k with mg over L, then you have this same expression for when you have a as you have a mass attached to a spring. Okay, so in that sense, then the pendulum can be also treated as a simple harmonic motion. In that sense, for the period of the pendulum, then will be 2 pi over 2 pi times square root of L over G. Okay, you replace K with mg over L, so the mm cancel out. Okay, and for this to be valid, your angle should be less than 15 degrees for small angle approximation. All right, so today we are going to check a physical pendulum. So if you have a physical pendulum, that means actually you cannot treat it as a point mass attached to a string, but this system also oscillates. Okay, so for example, like if you have a some kind of shape like this, then if this is the pivot point, the x rotation where it goes through that point, then if you pull this body to one small angle over here, you can again doing the free body diagram over here. So then on the center of mass here, you'll see there's mg here. You can resolve mg into two components. Okay, so mg cosine and then mg sine theta here. So this will be the net force because this force can be balanced out with a force going through this x rotation, but then this will not be balanced out. Okay, you'll pull the whole body towards to the equilibrium position, just as a pendulum. Okay, so you can take an equation, write an equation here. All right, so in this case, because the object will be rotating, so then we'll be checking this slightly differently. We are going to look at its angular or rotational displacement here, the angle theta. Okay, we are going to write theta in terms of the forces, or the torque in this case. We'll be looking at the rotational motion, right? So then let's take a look at what this force, net force, is going to, what torque is this going to produce? Okay, so this is mg sine theta times L. So L will be from the center of the mass to the axial rotation. Okay, so then L times minus mg sine theta will be the net torque. Okay, and according to the second law in rotational motion, moment of inertia times rotational acceleration, that should equal to net torque. Okay, and angular acceleration will be the second derivative of the angular position. Okay, so d squared theta dt squared, that's the second derivative of this angular position. So then that will be alpha. Okay, so then you replace alpha with the second derivative of the theta with respect to t. So then I times alpha becomes I times second derivative of theta over dt squared. Okay, that should equal to the net torque, which can be replaced with this expression over here, the minus L mg times sine theta. Now we'll take the small angle approximation here. So then sine theta can be replaced just by theta. Okay, so then it's minus L mg theta. Okay, now if you put I to the right hand side of equation, then on the left hand side you only have second derivative of the angular position divided by dt squared, that equals to minus mgl, right, divided by I, which is the moment of inertia of the physical body, times angular position theta. Okay, now compare this expression to what we have for the a simple harmonic oscillator, which is a mass attached to a spring, in which if you are looking for the x position, so second derivative of the x position over dt squared, that will be your oscillation, right? Oscillation is equal to minus kx over m, because force equal to m times a, and then force is also equal to minus kx. So then a equals to minus k over m times x, right? So these two expression has similar, or these two equation have similar terms or similar like operations, right? On the right hand side, it's both have second derivative to a quantity, okay? And then on the right hand side, you just have a constant term times the variable. It's the same here. MGL divided by I will be constant term, right? Because everything will be constant. It will not change with respect to the variable theta, okay? So then these two actually have the similar expression, okay? You can replace the K over X by MGL divided by I, then you will have the same solution for these two equations, okay? These two differential equations, all right? So for the simple harmonic motion, we had the solution as this guy if we use a sine cosine function. So x times t, x as function of t should be equal to a amplitude times cosine, okay, of omega t plus phi. All right, and then you can work on for the other quantities from that point on. Okay, and then you can also figure out what's the angular frequency, what's the period, and then the frequency as well. Okay, so similarly in this case for a physical pendulum, then the angular position as a function of time t should be also a cosine function. Okay, with an amplitude, which we just use the capital theta here represent for its amplitude. Okay, times cosine of omega t plus phi. Okay, so in the simple harmonic motion, which your angular frequency is what's listed on the bottom line here, omega equal to square root of K over M, okay? Now I say, I think I mentioned that we can replace K over M with the MGL divided by I, right? So then for a physical pendulum, its angular frequency then will be square root of MGL divided by I, okay? So that means in the solution here, this omega is this guy here, MGL over I, okay? So omega goes there, all right? And then once that's determined, you can have the period T as 2 pi square root of I divided by MGL, okay? So for a physical pendulum, the frequency or angular frequency will be determined by the mass, the M, and then the L, which is the, so L is not the length, the whole length. So keep in mind, this capital L is the distance from the axis rotation to the center of mass of the body, okay? So L is the distance from the axis rotation to the center of mass. And then I will be its moment of inertia, okay? All right. So with that, we can take a look on this example here. It says a physical pendulum consists of uniform rod of length D and a mass M. Pivot at one end. The pendulum is initially displaced to one side by a small angle theta and released from rest. Find the period of the pendulum in terms of the given variables. Okay. So you guys can work on this. We can take a look on the solution together, but I can also sketch the problem so we can get started here. So if this is one end of the rod over here, it's a uniform rod, okay? Now it can be pivot at this end. So that means it can rotate, okay? From this vertical, it's pulled to original angle theta over here and then released, okay? So the whole thing is distance d. So for a uniform rod, you can imagine that the center of mass should be at the middle, right? So then L will be equal to 1/2 D, okay? Because L is defined as from the center of mass to the pivot point, okay? The mass is the small mass. For a rod, if it's rotating with the one end over here, you can look it up. The moment of inertia is going to be 1/3 m, the mass times the length square, so md square, okay? So go ahead. It's looking for period. You can look it up in the previous slide. So period will be equal to, period will be equal to 2 pi square root of I divided by mg L there. Okay, so you can use that equation to start with and then express period in terms of D and M, I think, and then also G possibly, and then 2 pi or maybe pi. All right, so I think we can take a look on this together now. I see a couple of responses in. Um, so we basically have to replace I with this guy, and then L with this guy. Okay, and then we should be able to write an expression for our period after that. Okay, so square root of I, which is 1/3 md squared divided by mg d over 2. Okay, now you can see there's a couple of cancellations we can do here because a couple of terms here they can cancel out. So the first thing is the mass, right? So the mass here and mass there can cancel out. All right. The second thing is the distance d, the length of the rod d here. There's d here, there's d squared on top. So then this d will cancel out the square, leaving one d on the top there. Okay. So in that sense, then, but there's this 1/2 in the denominator will go up. Okay, so this guy will go up, and then this is 1/3 in the numerator, so the 3 can go down there. Okay, so a couple of flippings there too. So then your t should be equal to 2 pi square root of. On the top here, you should have 2d remaining, and then at the bottom here, you should have 3g remaining. Okay, so this should be your expression for the period t. Okay. All right. So just let me know if you have question on this one. I think one of the submissions you guys are very close. I think you're missing the 1/2 on the L. So L should be L is not again L is not the whole length of the object, but it should be the distance from the axis rotation to the center of mass of the body. Okay. And then the other response, I think you have plugged in this turns right, but you didn't do the cancellation of the mass. Okay, but that should be fine on that one. Okay. All right. So if you guys are clear, we can move on here. Another type of pendulum is called torsional pendulum. So it's a mass attached to kind of string or wire that you can actually rotate the body to sideways. Okay, so think about this. If this is like a probably like a metal string that is sturdy enough, but if you rotate it slightly, okay, then you'll expect actually there will be a torque movement making it go backward. Okay, so if this is again, if the torque produced by rotating this body to one direction is proportional to the angle, then you can write torque equal to minus, this symbol is called kappa. It looks like K, but kappa here. This is just to be, just to distinguish this from K, okay, when we have the spring, but this is the torsional, rotational, or the displacement here. So we use a slightly different notation over here, but the torque equals to minus kappa times theta, okay? So in that sense, you can see if you compare this with the expression we had earlier, torque equals to minus mg L theta. So mgl, they are all constant numbers. Then if you replace the mgl by kappa, then you'll get similar expression for the period of this oscillation. Okay, so in that sense, you can again start with I times alpha equals to torque. Alpha will be second derivative of the theta over dt squared. So then I times alpha, I becomes I times second derivative of theta with respect to dt squared equals to minus kappa times theta. Okay, similar expression we have earlier. So divide both side by I, then this becomes minus kappa over I on the right hand side. Okay, so And then you can also compare this differential equation to the differential equation we would have for the simple harmonic motion. And then in simple harmonic motion period is 2 pi square root of m over k. You can replace again k over m with kappa over I. So that means replace m over k here with I over kappa. Okay, so then period for a torsional pendulum will be equal to 2 pi square root of I. Again, will be the moment of inertia divided by the kappa. Okay, so kappa will be material dependent. Okay, all right. So that's two other types of pendulums. Okay, physical pendulum and the torsional pendulum. All right. So I think we are going to move on to the next section here in this chapter. Damped oscillations. Okay. I think this should be still chapter 15. I don't get the section number right, but it should be still chapter 15. Okay. So damped motion. So we say that when you have a oscillation, it will go back and forth, right? But actually, in reality, that really rarely happens because there's the resistant forces. Okay, for example, if you are going on a swing over here, which could be modeled as a pendulum or maybe a physical pendulum, but when you start to swim, if you do not get other pushes or somehow manage to use your chemical energy in your body to kind of swim, and you will eventually the swing will eventually stop, right? So that's because the air resistance is in play most likely there. So in reality, this is what's most likely. So if you look at the amplitude of the oscillation, you'll see that the amplitude actually dies out as a function of time t, all right? But then if the air resistance is small enough, okay, or if it's not substantial, then you will see that the period actually doesn't change quite much, okay? So the period appears to be stay the same as if there's no resistance or no damping, okay? So this is what you would have. And then now let's take a look on the dynamics of that oscillation. So then we'll be looking at net force, okay? Net force is m times a. That's going to be equal to, so for the system showing in the previous figure, you'll have minus kx that's coming from the spring, and then minus b times v, velocity dependent air resistance or the fluid resistance in this case, okay? So then this is the second force. So mass times acceleration then equal to minus bv minus kx, okay? So you have extra term of minus bv here. All right, if you rearrange the terms, A acceleration can be rewritten as double derivative of position over dt squared. So that's A, okay? So m times A basically is this term, and then you move this term to the left-hand side of equation, minus BV becomes positive BV, right? And then you rewrite BV as derivative of x over dt, so plus b dx dt, okay? And then move this guy also to the left-hand side, becomes plus kx, okay? Equals to 0, all right? I'm not sure you guys have learned how to solve a differential equation yet of this type, but the solution for this differential equation would be this guy here. Okay, so it's a cosine function, all right, as what a simple harmonic motion would have. So cosine omega t plus phi, all right. And then original amplitude A0 comes in here. Now with this damping factor, the amplitude decreases with this exponential function e to the minus b divided by 2m times t. Okay, so if you would plot this x over t, x as a function of time t, then it would look like this figure in the previous slides like this. Okay, so it goes down, the amplitude goes down. Okay, the cosine function still remains there, all right? And then in this case, the omega is going to be equal to square root of k over m. This is the original omega 0, okay? Minus a term called b divided by 2m to the square, okay? So in that case, you can see if b is small, then your frequency doesn't really change much, or the period doesn't really change much, okay? So if you plot this guy, then it looks like a figure, I think in this size over here. Okay, so I think it's better to have this one show up first. So this is then what will be what you have. Okay, so in the within the brackets of the exponential decay, then you still have the cosine function. Okay, so the decay is the amplitude decays down like that, and then the cosine function still remains there. Okay. So the original square root of k over m is called the natural frequency, natural angular frequency. Okay, and then this is the actual frequency for the damped harmonic motion becomes this guy. Okay, so then becomes this here. All right. Again, as I mentioned, depends on the damping factor, which is determined by B. So if B is small, it's less than, or B squared is less than 4mk, then you will still have a kind of oscillation like that. The cosine function, but the amplitude dies out. Okay. If B equals to, or B squared equals to 4mk, then it actually dies down quickly. All right. And then if it's greater than 4mk, then it also dies out quickly. Okay. But as not as much as this guy. Okay. All right. So it depends on how strong is your damping factor. Okay, so let's take a look on this one here. This example here, it says the amplitude of lightly damped oscillator decreased by 3% during each cycle. What percentage of the mechanical energy of the oscillator is lost each cycle? Okay. So you guys can give it a try. So, but basically, if you remember, in the first or second section of this textbook, it says that the mechanical energy of the oscillation is equal to 1/2 kx squared, right, plus 1/2 mv squared, and then that's equal to 1/2 k amplitude squared. Okay, so you can actually relate the mechanical energy as this guy. Okay, so in this case, if this decreased by 3%, then how much mechanical energy is being decreased. Okay, so give it a try. We can take a look on the solution together in a little bit while later. Just a few, probably a few minutes later. Okay. All right, so let's take a look here. So as I say, you can relate E as 1/2 Ka squared, right? So the initial mechanical energy then will be 1/2 K A0 squared. Then let's use A0 for the initial um, magnitude. So then after one cycle, let's call it E1. That should be 1/2 K A1 squared. Now this time A1 will be equal to it's decreased by 3%. So it'll be equal to 1 minus 3%, right? Times A0. So which is 0.97 A0. Okay. So it's asking you how much percent decrease will be the energy. Okay. So then we have to see what's this in terms of initial energy, right? So we want to see what's E1 by E0 now, and then do 1 minus of that, and then express that in terms of percentage. That will be the last of the energy in percentage. Okay, so this will be 1 minus E1 will be now 1/2 K times A0 will be 0.97 A0 square divided by 1/2 K A0 square. Okay, so you can see that 1/2 K and 1/2 K will cancel out. Okay, the A0 square and A0 square will cancel out. Okay, now here you should have 0.97 squared. Okay. So this is going to be equal to 1 minus 0.97 squared. Okay. Then it turns out this is going to be 0.0591. Okay. And then in percentage, this is 5.91%. Okay. So it's not exactly 6%. Okay. It's less than 6%. So this will be your last percentage lost. Okay. Um, You can also expect if after the second cycle, then it's not going to be 9% lost. Okay, it should be a little bit less than 9%. Okay, etc. Because yeah, actually, the amplitude dies out actually not linearly but exponentially. Okay. All right. You can let me know if you have questions. Okay. All right. So if you guys are clear, we can move on here. Um, So on the opposite side, on the other hand, you can actually force oscillation, right? So you can give a driving force in addition to the oscillation. So you can just give it a driving force, like use your finger like that. Okay, so it depends on the frequency that you are driving this guy. If you are happens to have the frequency that is equal to the natural frequency of this oscillator initially, then the amplitude of this one will be amplified largely. Okay. On the other two scenarios, if you have lower frequency or higher frequency, then amplitude will not be changed too much. Okay. All right. So in this case, let's take a look example as shown in this figure. So you can actually drive this oscillation by having this guy rotate with the angular frequency omega. Okay. So if this omega matches up with the natural frequency, then this will be the oscillation will be forced. Okay. So you'll actually um, resonant. Okay, so then the amplitude will be larger. Okay, so in this sense, let's take a look on the Newton's second law, the force, the dynamics over here. So net force is equal to ma. All right, a is derivative. If this is one dimensional, so then it's just derivative of x over dt squared. Okay, we can call the vertical to be x. Okay, because this is just one dimensional. So you can call it y if you want, but doesn't really matter. Um, now the net force should have, in this case, you will have the force by the spring constant, okay? And then there will be the resistance from the fluid. So again, this will be minus B times V, okay? This will be minus KX, okay? The mg is already canceled out by the original equilibrium position at the equilibrium position. Like you can see this will be not the natural length, okay, for the equilibrium position, it should be elongated by kx naught, which is equal to mg. So then the mg will be already included or cancel out by the pick of your equilibrium position. Okay, so you'll be picking not the natural length to be the equilibrium position, where it will be the origin, but some position below it. So then kx will be equal to mg. Okay, or kx now be equal to mg. So in that sense, you will have just consider those two forces, and then the driving force. Okay, so if the driving force, if this is rotating, you can use a sine function. Okay. So again, for the solution to this, okay, it will be a cosine function. All right, with a, the amplitude, that is equal to f0 divided by square root of m omega square minus omega 0 square plus b omega square. Okay, so you can see from this expression over here, so if omega matches with omega naught, which is natural frequency, then amplitude will be the maximum, right? Because then this guy goes to 0. Anything else, smaller omega or larger omega will give you a non-zero term here, okay? Then a will be smaller, all right? Okay, so if you have, it depends also on damping. Okay, so if you have small damping, then the amplitude will be the maximum. If you have medium damping, and then heavier damping will be giving the minimum amplitude. Okay, as we would expect it. Okay, all right. So lastly, I want to show you this video over here. So this is the bridge, Tacoma Narrows Bridge in Washington State, and that was in 1940. It actually collapsed because at that particular day the wind matches with the natural frequency of the bridge. Then it actually oscillates. So then the oscillation amplitude actually builds up. Okay, so then there's a lot of mechanical energy in the bridge. It vibrates a lot, and then eventually it breaks down. Okay, so let's take a look on that video here.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders, others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
All right, so I think so since then people have learned the lessons to consider the natural frequency of the bridge. Okay, so I think that will do it for today. Okay, so tomorrow we'll take a look at a couple of examples, and then that should do it for this semester. Okay, so I will see you again tomorrow in class. Okay, bye bye. All right, so you're looking, I got the question here about final exam cumulative of just about most recent chapters. It will be the most recent chapters as usual, but we'll probably use some of the concept that we learned before, okay? But emphasis will be on the most recent chapters, okay? All right, great, see you then.